Hello there, welcome back. This is the last lecture of week 8, short one, where we recap the coverage criteria that we saw and look at how it's applied on a few examples that we've seen earlier. So these are the 6 coverage criteria for input space partitioning or equivalence space partitioning that we saw. All combinations, which blindly considers all the combinations of all the partitions of inputs. Each choice, which considers one randomly chosen choice per partition of the input. Pairwise, which considers partitions of inputs at pair at a time, but that is for test requirements. Test cases could consider all the input spaces. So you can meet pairwise criteria faster with lesser number of test cases. T-wise is an extension of pairwise for any number of combinations of inputs that you want to consider as a subset. Considered not very useful. Multiple base choice and single base choice coverage lets you handle one particular input or more inputs with base choices as partitions, specific partitions for those inputs, and let the other partitions over the other inputs vary. And this is the subsumption criteria. What we will do is we will apply it to the testing of this triangle method. You remember this program? We saw it as an example of logic coverage criteria. It's a method that takes as an input 3 sides of a triangle, side 1, side 2, side 3, and based on the properties of the 3 sides, it outputs whether the triangle is of type scalene, isosceles, equilateral, or if it is not even a valid triangle. So this is the type of a triangle program. At that time, we had applied logic-based criteria because this had all these decision statements. We considered the predicates, we solved for the internal variable, did reachability, and so on. Now, we are going to test the same method, but not by looking at its source code. We could even draw a control flow graph if we look at its source code or apply logic-based criteria. We are not going to do that. We know that this is a method that is supposed to take 3 sides as input and output the correct type of the triangle, classification of the triangle. So this is the tri-type program. What we want to test for now is black box testing by partitioning these 3 inputs appropriately. So the 3 inputs are the 3 sides, and the output that is expected is the type of a triangle, either scalene or isosceles or equilateral or not a valid triangle. We know this much. This is the requirement of this method. We're not going to look at the source code of this method. We will design black box test cases by applying coverage criteria that we learned just now for the same method. How are the coverage criteria going to look like? Let's consider ACOC, all combinations coverage criteria for the same tri-type triangle. So there are 4 partitions that can this is just a random choice of partitions that I am doing. So if the length of the side could be greater than 1 or equal to 1 or equal to 0 or less than 0. In equal to 0 or less than 0, you should get it as an invalid triangle. If it is greater than or equal to 1, then it classifies based on the kind of input. So this is some partition for the sides that I'm considering. That tri-type method had 3 sides. Per side, I'm considering 4 partitions. What are the 4 partitions? The length of the side is greater than 1 or equal to 1, or the length of the side is equal to 0 or negative. So based on these 4 partitions, there could be 64 different test cases that will satisfy all combination criteria, right? Each of them corresponding to 1 side. Here are some of the tests. I have obviously not listed 16 of them here, 64 of them, but here are some sample tests requirements. So 2, 2, 2 means all sides have length greater than 1. 2, 2, 1 is side 1 and side 2 have length greater than 1. Side 3 has length equal to 1. Similarly, 2, 2, 0 is side 1 and side 2 have length greater than 1. Side 3 is length equal to 0 from the third partition. Sorry, there should be a missing closing parenthesis here. Please add that. and so on. Similarly, the last one, 2, 2 minus 1 is side 1 and side 2 having length greater than 1, side 3 having length less than 0. Like that, you can go on considering various combinations. Like for example, if I take the third item here, 0, 2, 2 indicates side 1 is length is equal to 0, sides 2 and 3 have length greater than 0. Same for the second test case. Third one, 0, 2, 0 indicates that sides 1 and 3 have length 0, 2 is greater than 0, and so on. So these are the different combinations that you can consider. Obviously, as you see, it's all combinations coverage criteria. So even for a simple program like type of the triangle, you get too many test cases. So let's try to apply some other combination. So let's consider pairwise criteria. So as we told you, there are 4 partitions for each of the sides: greater than 0, equal to 0, less than 0, equal to 0, equal to 1, greater than 1. So if I consider pairwise, there should be 16 different test cases to satisfy pairwise criteria for this method. Here is one such possibility. So this full set gives me 16 different test cases. And let's pick up something and understand. So 2, 2, 2, all 3 sides have length greater than 1. That's the partition that it belongs to. Then 2, 2, 2 is paired with 2, 1, 1, where 2 is fixed and 1, 1 says the first side has length greater than 1, the other 2 sides have length equal to 1. Similarly, the third test case here says first side has length greater than 1, other 2 sides have length equal to 0. The fourth one is the last in that pair. First side has length greater than 2, the other 2 sides have length less than 1. Less than 0. Of course, you can give any negative number here, it doesn't matter. Similarly, here for being greater than 1, you can give any number, not necessarily 2. This is just a sample. Similarly, the next one fixes 1 for side 1 and varies the other 2 sides: 1, 2, 1, 1, 2, 2, 1, 0, minus 1, and 1, minus 1, 0. The remaining 4 fixes 0, which is from the next partition for side 1 and varies the other sides. The last 4 fixes minus 1, which is the fourth partition for side 1 and varies the other sides. So this follows pairwise coverage criteria and results in useful lesser number of test cases. The next, just as a sample, let's look at multiple base choice coverage criteria. So let's assume as of now that side 1 is my side that I'm going to fix. And let's consider 2 and 1 to be the base choices for side 1. So this gives us 2 base tests. That is, side 1 is 2, side 1 is 1. The other 2 tests are 2, 2, 1, 2. 1, 2, 2, 2, 2, 2. I have just chosen 2, 2 for both of them. So totally how many we will get? This 2 and 1 are base choices for side 1. So I keep these 2 test requirements aside. So that's this 2. Then vary the others. So that will be 6, 6, 6 respectively, 20 different test cases. If you list them, you will find that there are some repetitions. So we will get 16 unique test cases, reasonably similar, not in terms of the exact test requirements, but in terms of the number, it's exactly similar to pairwise criteria, just specifically for this case. So here what we did was, we took the same tri-type triangle, but we subjected it to black box testing. We looked at the inputs, we looked at the expected output, and applied the coverage criteria that we learned on the inputs. So you could in general do it for any method, provided you know the functionality of the method and what it's supposed to do, design some test cases. So here we chose things like equal to 0, less than 0, because in those cases it's supposed to output an invalid triangle. So those are useful partitions to consider. So like this, based on the functionality of the method, without looking at the source code of the method and knowing the inputs to the method, you can still define very useful test cases. So I'll show you one more example. So let me just go to that particular slide first. If you remember, we had introduced this finding an element in a list. Again, didn't have the source code, but yeah, so this was the thing that we had. We looked at this method whose source code was not given, find element, it takes two arguments, two inputs. One was the list, the other one was the element to be found in the list. So if the element is found, then you return true, otherwise you return false. If the list or the element is null, then you throw a null pointer exception. This was the functionality. We are doing black box testing. We would like to design test cases based on input space partitioning for this method. So let's see how that goes. Again, let me switch over to the slide directly. Yeah, so this is for find element. So here what will happen is, I'm illustrating a possibility of a test case when we try to partition the input. By the semantics of what this method is supposed to do, some partitions that I come up with can immediately become infeasible. So how does that happen? So remember, this find element takes two inputs, list and an element to be found in the list. So let's say I choose some characteristics. So I say the first characteristic I choose to partition would be the length of the list and maybe the contents of the list. What is the property of the list? So I could say the list has exactly one element, that gives rise to one partition. The list has more than one element and the elements are not in any sorted order. That gives rise to second partition. The third partition says the list has more than one element, but they are all in sorted order. The fourth partition says the list has more than one element, but the elements are just replicas. They repeat themselves. All of them are the same element. Just some choice based on the characteristic of the length of the list and some property about the elements that you can find in the list. Exactly one, more than one, unsorted, sorted, and identical. This is one partition that you can think of. It's a valid partition. It's disjoint and it's complete in terms of spanning this input space. I could partition it in another kind of characteristic. Let's say match. That is the element found in the list? Yes or no? So I will match it based on that. So one partition is element is not found in the list. The next is element is found, but it's found once, exactly once. The third partition is element is found, but more than one occurrence of the element is found in the list. So these are the three partitions. If you see, you obviously get some invalid combinations. You can't blindly apply pairwise or all combinations criteria. Some invalid combinations are A1 and B3 and A4 and B2. Let's see why they are invalid. What does A1 say? A characteristic, length and content. Partition 1 says the list has exactly one element. What does B3 say? It says the element was found more than once in the list. So when the list has exactly one element, you cannot consider another characteristic which partitions it as the element found more than once. So A1, B3 is not going to be a valid combination to consider. Similarly, A4, B2. A4 says the list has more than one element and all of them are identical. And B2 says the element was found once in the list. So if the list has more than one element and all of them are identical, it cannot be the case that the element is found exactly once. So A4, B2, characteristic A, partition 4, is not consistent with characteristic B with partition 2. So these are invalid combinations. So the presence of these invalid combinations, I'm partitioning the same input space, by the way, list and element, in two different characteristics and trying to consider combinations of these partitions. I could do this, partitioning the same input space using different characteristics and testing their combination, or I could consider partitioning one input at a time and considering each of those combinations of input. Either way, I can apply input space partitioning. In this case, if I take the same input and consider two different kinds of partitions based on two different characteristics, I do get invalid combinations. So what is the way out? The way out is, so these are the problem. Constraints are relations between partitions from different characteristics. Basically, they indicate a block from one characteristic can never be combined with a block from another characteristic. Sometimes the reverse is also useful. If you combine a block from one characteristic, take a block from one characteristic, it must be combined with a block from another characteristic. Like for example, if the list is such that the element is found more than once, then you can take only partitions 2, 3 and 4 for A. You cannot take 1. So that's what it says. So whenever you have these constraints, and you can't take these purely syntactic coverage criteria like all combinations coverage, pairwise coverage and t-wise coverage. If you take them, then you have such constraints as we saw in the example, you just drop it. You can't make them feasible at all because they correspond to invalid combinations. But if you choose base choice or multiple base choice coverage, maybe you can handle some of these cases by altering the base choice to make sure that the infeasible constraints don't come. Like for example, I could consider here the base choice as like for example A1, B3, if I take this, I could consider the base choice as element is not found or element is found once. I remove this base choice. So if I consider multiple base choice coverage, in the presence of constraints, I might be able to consider invalid combinations, but the other ones like all combinations criteria, pairwise coverage or t-wise coverage are purely syntactic notions. So they will not be able to cater to infeasible constraints like this. You just have to drop them if you consider. So I hope this example was useful in terms of illustrating how to apply input space partitioning to get black box test cases. In general, all that you need is what is the functionality of the application or the method under test and what are the types of inputs. And based on the functionality and the data types of inputs, you come up with useful partitions and apply any of the suitable coverage criteria that you can think to do partition based coverage. So this would be the end of black box testing for now. Next week, we will move on, week 9, and look at a new module. I'll stop here for now. Thank you.